Great, thanks for the introduction. And thanks everyone for making it through this long program and tutorial. So I'm excited to close it out. So I wasn't quite sure what to talk about for my second tutorial. I mean, I knew for my first one, I wanted to talk about tensor decompositions. And then I got so many great questions, so many long emails about the ins and outs of Jennrich's algorithm that I came to the conclusion you guys really like tensors. So I'm going to give you a talk about tensor completion, which is another basic problem in data science that has to do with tensors. It has a pretty different character than the tensor decomposition problem. But I think what makes this so intriguing is that there's so many different connections. So I'm going to introduce tensor completion, and I'm going to talk about this amazing world of refuting random CSPs and what it has to say about basic inverse problems over tensors. So this one is really going to be a synthesis of a few different viewpoints, coming together on this problem. So I'll go slowly, as I always do, or try to, and let me introduce at least some of the motivation. In fact, before we go to tensor completion, let's talk about matrix completion. And one of the main motivations for matrix completion came from this now pretty famous Netflix challenge, where they released a bunch of data, and you can think about it as being organized into a matrix where the rows represent different users and the columns represent different movies. And the entries, when there are entries, when you get an observation, it's just a numerical rating between 1 and 5 stars of how much the user liked the given movie. So Netflix released this data set, which had about 500,000 users and about 20,000 movies. And they, put out the challenge of, can you design a better recommendation system than what they currently had? And one of the ways that people approached this problem, there were really many ingredients into the overall solutions that met their challenge. One of the main ingredients was matrix completion. Now, one thing that I want to tell you about the data set, which is sort of a little bit less well known, was that, you think about this as being a large, very sparse matrix. It's actually not as sparse as you would think. So the actual data set that Netflix released was about 1% observed, which is pretty crazy because it means that the average user was rating some, giant number of movies. So the average user was rating something like 200 movies. So this was a very hand-picked set of, the densest part of their real problem. And there are a lot of interesting quirks about this data set too, because in the final solutions, people had to, do all kinds of interesting data cleaning aspects. Like they figured out that, the movie Napoleon Dynamite should just be treated like no other column in this matrix because it just behaves totally randomly, whether you like it or not. In any case, the basic mathematical problem that we're interested in is just, can we approximately fill in the missing entries? Now, you have to assume that somehow the unobserved entries are well structured in some way, that at least the entries you are observing give you enough information to piece it together. So the usual assumption, which is not literally true, but might be approximately true, is that M is unknown and low rank. Now, the way to think about this is if I give you this matrix M, which imagine I totally observed it, I knew for every user how much they liked each different movie in the collection. Well, if you think about the rank 1 matrices in this decomposition, you're hoping that they represent different categories. So for example, one of the categories might be drama. And then you have this column vector times this row vector. So this column vector, remember, M is indexed by the different users. So this vector might represent how much each user likes movies that are in the category drama. And then this row vector that I'm multiplying by might represent for every different movie, how much does that movie appeal to someone who likes movies that are about drama? And the hope is that somehow the low rank decomposition of this matrix really has to do with the underlying categories of your data set. In any case, this is where the low rank assumption comes from. And the basic model, which is intended just as a simplifying assumption, it's not designed to be literally true, is that you assume that there's this unknown low rank matrix M, and the entries you do observe in your Netflix data set are really uniformly random observations. So someone picks uniformly random among all IJ pairs, some user movie pair, and they show you how much that user likes that given movie. And the basic question is a really beautiful algorithmic question. Is there an efficient algorithm to recover M, even though you're seeing just a vanishing fraction of the entries of this matrix? So there's one way that you can think about setting up this problem is the following optimization problem. So omega is going to denote the set of observed entries. So it's a subset of the row column pairs. And what you're going to do is you're going to look for a matrix X that agrees with the underlying matrix M on all the entries you observe. Maybe you put some sort of upper bound that it approximately agrees on average. But among all of these valid X's, you're going to look for the one that has minimum possible rank. So this is an optimization problem that you'd love to solve. But the trouble is that it's non-convex, and it really is an NP-hard optimization problem. So there's really no hope of solving this problem, at least in a worst-case sense. But the important thing about matrix completion is that there is a powerful convex relaxation. So that's what I want to explain to you is what this convex relaxation is, where it comes from, and what it does. Because when we move to tensors, all of a sudden the story is going to become much more complex and there'll be new ingredients in it. So the way that this relaxation comes about is if you take your matrix X, this is some candidate hypothesis that, let's say, agrees with the observation you're given. Well, what you can do is you can take its singular value decomposition. So you're writing X as the product of U times sigma times V transpose, whereas usual, U and V are orthogonal, and V is this diagonal matrix. Even though it's rectangular, its only non-zeros are along the diagonal, and those are called the singular values. So let's let sigma 1 up to sigma r denote the singular values, and everything after that is 0. So now knowing the singular values tells us a lot about the matrix X, because the number of non-zero singular values is exactly the rank of X. Now, I just said that it's hard to work directly with the rank. It's hard to look for the X that has smallest possible rank that agrees with my observations that I've seen. But instead of using the rank, which is the number of non-zero singular values, well, you do the usual replacing L0 with L1 trick. That's the thing that comes up in things like compressed sensing. And what this means in this context is that instead of trying to minimize the rank, we're going to try and minimize the sum of the singular values. That's called the nuclear norm. So that is a convex optimization problem now. As you look among all the X's that agree with your observations so far, that's a convex set of constraints, no problem. And you now have a nice norm, the nuclear norm. You're minimizing among all X's that agree with your data, which one is the simplest according to this norm. So this approach was introduced in a really important thesis of Miriam Feisel. It was analyzed over a sequence of works with different kinds of guarantees. Cerebro and Schreidman, Recht, Feisel, and Perlow studied something called matrix sensing, which is a related problem. And then there were some very important works of Candice and Recht and Candice and Tao that seemed to nail these things with important contributions of Gross really along the way, which are the main ingredients in, for example, in the Candice-Recht proof. So the matrix M, the main theorem, the meta theorem from some of these works is that if you take a matrix M, and let's say it's n by n just for simplicity, because I want to minimize the number of parameters. So if it's an n by n matrix and it has rank R, now you need another condition to be able to hope to recover it. Because, what if the non-zeros in M were not spread out? Like, what if they all happened along the diagonal of the matrix? Then if you're observing uniformly random entries of M, you would just never see those non-zeros because they're too sparse. So instead, what you do is you assume something called incoherence, which has a few different instantiations. Usually it means that the non-zero entries are spread out in some way across the matrix, or that your singular vectors are not aligned with the standard basis vectors. In any case, it's a very natural condition that a random matrix would satisfy. And the important thing is that if you're low rank and incoherent, then you can get by with roughly n times r observations. In particular, this convex program that I described for you exactly recovers the low rank matrix just from so few and so sparse observations. Now, just to emphasize, what's amazing about this result is if I have a rank R matrix, how many parameters does it have? It has n times r plus r times n. So it's got 2 times n times r parameters, roughly. So here we're getting by with almost as few observations up to logarithmic factors as there are parameters in our model. We're getting around the fact that we can't solve this non-convex NP-hard optimization problem, and we found a good convex surrogate that does almost as well. So this, as I was mentioning, is nearly optimal since there are O of n times r parameters. Okay, but this workshop is about tensors, so let's talk about tensors. In fact, what I'll really be interested in is what happens when you try and complete objects with a higher order structure, even just third order tensors, but they'll all be low rank, just for simplicity.
Ankur, there's a question from Adina. Yeah, go ahead.
Yeah, thank you. I just wanted to ask, is there any guarantee between the convex solution and the optimal L0 solution?
Yeah, that's a great question. So they will coincide in these settings. So the NP hardness, it's something that isn't such a barrier to these nice average, these nice problems once it's sort of better posed and the entries are spread out, and that's great. But the only, I think that's what's cool about it is there are interesting models where you still can compute it. It's just that the nuclear norm sort of gives the right intuition, I think. Great. So now what about tensor completion? So can we use more than 2 attributes in recommendation systems, and can it lead to better recommendations? So actually, there's a kind of fun example that I like for this, which is let's take something like Groupon, right? So, back in the days before COVID, I'm told people used to go out and do things, maybe even in groups sometimes. And it would be good to sort of recommend people different activities they might like. So you once again have this recommendation problem because you have a collection of users using Groupon and you have all of these different activities you can advertise to them. But what I claim is that there are situations, especially like Groupon, where there are extra components of your problem that if you can incorporate them, could make your recommendations all that much better. So for example, Groupon advertises things like skiing, right? Which in the Northeast where I live, that seems like a year-round activity because we always have snow. But in other places I hear, like in LA, apparently the weather is nice and you shouldn't advertise skiing. So in any case, we can really think about this as being organized as a tensor now, because we might have users and activities in a different time period also, right? So we only want to recommend activities which are relevant in the given time. Now, the same intuition that I gave you for why this underlying matrix would be approximately low rank because of the categories of different movies people like and the things that they fit into, we can think about the same reason leading to this underlying tensor as being approximately low rank. Because now it could be something like one of the terms in the low rank decomposition. It could be the outer product of 3 vectors, and it might represent a category like snow sports, because you might have something like, which users like snow sports, which activities are about snow sports, and what time of the year is the right time to do snow sports. So I think it makes a lot of sense to study tensor completion, especially from the perspective of recommendation systems. There are tons of other motivations for tensor completion that are, interesting in their own right, but I wanted to give you a more data science one motivated by the reasons for matrix completion. So the basic question we can ask now is, can we complete low-rank tensors from very sparse sets of observations? Very basic problem. So can we approximately fill in the missing entries? Now, there's a big problem with tensors, is that many of the natural things that we'd like to do with matrices just don't work. And that's something we have to deal with. We have to tackle head on. So, there is something you could try, which is there's the nuclear norm for matrices. So I guess the natural thing to do is to look at the tensor nuclear norm. Now, it's not so important for this talk what exactly the tensor nuclear norm is, because that's not the thing we're going to do. But just to be clear, let me give you some intuition. So for matrices, when you look at the set of nuclear norm at most 1 matrices, that itself is the convex hull of A times B transpose, where A and B are unit vectors. The tensor nuclear norm is the same thing. The set of tensors whose nuclear norm is at most 1 is the convex hull of A, tensor B, tensor C, where A, B, and C are unit vectors. So it's a very natural convex relaxation to the set of low-rank tensors. This is something that people tried many times over, was to just use tensor nuclear norm and try and complete tensors as if there are no problems.
Ankur, there's a question in the chat from Cynthia Zhang, who says, here you're using the CP rank to describe the low rank condition. Would you elaborate on other rank decompositions, e.g. Tucker rank?
Yeah, that's a great question. So Tucker rank, I think, I have to think about it. So I'll see if I can find some papers and see if I can send you the link, but I know that problem has been studied. I think it is a very different character problem than the CP rank, and there's some ways in which it's a bit easier. So I'm not sure I'm going to be able to give you a great answer right now, but thanks for the question nonetheless. So there's a big problem, which maybe many of you have anticipated, which is that, the tensor nuclear norm is NP hard to compute. Actually, the first place where this showed up, the NP hardness, was in a paper of Gurvitz, and it's related to quantum. Because, when you go to fourth order tensors, the tensor nuclear norm is sort of intimately related to the notions of separable states, and deciding approximate membership in the set of separable states is something that, the quantum folks, especially the quantum information theorists, have a very precise understanding of many aspects of it. And in fact, there's a sort of meta reason why you wouldn't expect that to work. It's just because most of the linear algebra toolkit kind of goes out the window once you look at tensors. So I think Hiller and Lim put this best, because the title of their paper, which says it all, is that most tensor problems are NP hard. And if you don't believe the title, you can just go through and look at this compendium of, all your favorite problems that you wish you could solve, and all the negative statements about things that you can't do. So tensor nuclear norm is just going to be a non-starter for us. Actually, I'll give you some reasons connection to random CSPs, which tell you why you wouldn't even hope that you could approximate it in any meaningful sense. Because the truth is...
Sorry to interrupt. There's another question in the chat from Hiro, who says, what exactly is the definition of the tensor nuclear norm?
So it's the smallest C, so that your tensor fits into the C dilation of the convex body. That's the convex hull of A, tensor B, tensor C, where A, B, and C are unit vectors. So you can check that, for matrices, if you did the same thing, if you looked at the norm, which is the smallest C, so that my matrix fits into the convex hull of A, tensor B, where A and B are unit vectors, that it coincides with the sum of the singular values. Because in fact, when you write the singular value decomposition, it is explicitly a description of how exactly to fit in the matrix into the dilation of that convex body. So we will get into that a bit more later, because I'll need to know what the matrix nuclear norm looks like later on. But the tensor nuclear norm, we're not going to use it because it's hard. In fact, it's even hard to approximate in a lot of reasonable senses. So, as I was saying, most tensor problems are NP hard, and we're going to have to find some other route to doing tensor completion. So let's try and do something trivial first. Let's try and do not too much work. Well, we saw through Jennrich's algorithm that, sometimes you can get interesting algorithms in the land of tensors just by turning them into matrices, by flattening and doing something anyways. So let's try and do that first. So many tensor methods, things like Jennrich's algorithm, do rely on flattening. Let's flatten a tensor and see how well we can do. So imagine that my tensor is n1 by n2 by n3. Well, I can flatten it into a n2 times n3 by n1 matrix. And what this would correspond to in our Groupon setting is it's flattening it into a user by activity cross time. So this is not good intuitively, because now you're doing a recommendation system that ignores the structure of the fact that it's the same activity happening at different time periods. You're treating each activity time as a completely algebraically new thing, which are not using any relationship between them to get any sort of good recommendations. Now here, what's going on, of course, I think everyone in the audience knows this, but you're just taking the tensor Tijk and you're reorganizing its entries so that the ijk entry goes in the row corresponding to I and the column corresponding to the pair jk. So this rearrangement of entries into a matrix, it doesn't increase rank. Sometimes it can drastically reduce rank, but it's kind of obvious just from this multilinear description of what's going on that you could just take your factors B and C, take their outer product with each other as a matrix, reorganize that into a vector. And this is very explicitly a valid decomposition of the flattened tensor. So hence it gives an upper bound on the rank of this tensor. Not saying anything very surprising here or deep, but let's return to this inverse problem. So let's make our lives simple. N1 equals N2 equals N3 is N. So how many observations would we need to fill in this flattened tensor if we completed it using matrix completion? I claim we'd need n squared times r observations because that's the number of parameters in our low rank matrix model. One of the dimensions of this matrix is n squared. And so just from that part of the low rank decomposition, you'd end up with n squared times r parameters. Now, there are many other works that actually, there are tons of works on tensor completion. Many of them really just use variants of flattenings because maybe you flatten it one way and then flatten it another way and then, find some way of averaging their nuclear norms, right? And there are a lot of empirical studies of how well this does, and it gets you better constants really for small problems, but it's not going to get you better than that. So the main question I'm going to ask is, can we beat flattening? So can we complete tensors better than treating them naively as matrices? And to put it back in our data science problem, can we make better predictions than we do just by treating each activity cross time entry as being totally unrelated? So let's talk about some of the main results, but then I'll survey what else is known about tensor completion because there's still many open questions in the space. But let's say that we get m noisy observations from the tensor T. So I'm even allowing some sort of additive eta amount of noise. And let's say that all of our vectors, all of our factors, the a sub i's, they have infinity norm bounded by C. You could instead treat the AIs, BIs, and CIs as unit vectors, but then you have to carry around a lot of different normalizing constants. So let's just assume that they're bounded by some parameter C, so that the typical entry is happening something at the constant scale. Then what we showed actually a few years ago, this was back in 2015, was that there's an efficient algorithm that outputs and that circumvents the hardness of tensor nuclear norm, that outputs a tensor X, which has the property that the average error on a typical entry behaves like root of n to the 3/2 over m. So the important thing here is that as m beats n to the 3/2, you're getting vanishing error, at least for constant rank tensors. And when you think about super constant rank, then you need m to depend on r as well. So this beats flattening in the sense that we don't have n squared, we have n to the 3/2. But now something totally wild happens, which is that I think it would be easy to look at matrix completion and, more generally the set of linear inverse problems that people study through convex programming and think that you can do it all, that, you can always reach the statistical limits algorithmically. That's not true for tensors. So not only is the tensor nuclear norm hard to compute, but as for reasons that I'll show you, and this is my main point in this talk, it's actually connected to a classic problem in probability and theoretical computer science, which has to do with refuting random CSPs, in particular random 3-SAT. So what we showed was that if you can solve noisy tensor completion, even when you just have some pretty trivial tensor, if you could do it better than n to the 3/2, you would get better algorithms for refuting random CSPs than are conjectured. And there are many types of evidence showing that n to the 3/2 might be the right threshold for random 3-SAT. So to a certain extent, one of the amazing things I think is that for tensor completion, it's a fairly salient example of a natural inverse problem on tensors, where there's actually a fundamental computational versus statistical trade-off. You can beat the naive algorithm of flattening, but you cannot get all the way down to the information theoretic limits. Not just because tensor nuclear norm is hard, but because even the problem it's trying to solve, even approximately, even if, under many conditions, it's a very hard problem. So, I'm going to go slowly because I'm going to have to connect tensor completion to a lot of other worlds. That's all I'll be doing is, in fact, I'm just going to talk about matrices and explain this connection in the context of matrices. And only later will I tell you what this reinterpretation gives us in terms of new algorithms for tensor completion. So first, I'm going to study an even simpler problem than completing a low-rank matrix with noise or a low-rank tensor. I'm actually just going to ask for something that's called a distinguishing problem. So I give you samples that are partial observations of a matrix, and I promise you that they're generated in one of two ways. These ways will be very different, but I want you to efficiently tell me which of the models it's coming from. That's a distinguishing problem. So case one is, imagine I take a rank 1 matrix even, so A times A transpose, and I add some kind of noise to it, and your observations come from this model, rank 1 plus noise. Now, to be precise, I'm going to need a very particular rank 1 matrix and a very particular notion of noise in order to build this connection to random CSPs. But what I'm going to do is imagine that this vector A is a random plus minus 1 vector. Now, if you think about Mij, it should be the ith entry of A times the jth entry of A. So just the product of these plus minus 1 entries. And that'll be the true entry in M with probability 3/4. And with probability 1/4, I'll instead give you something noisy. So it's a noisy measurement instead, and it'll be a random plus minus 1 label with probability 1/4. So that's one generative model. The other generative model will be very similar, except for the fact that there is no signal. It's just complete noise. So each time I give you an entry of M, it is a random plus minus 1 entry. There's absolutely no structure to it. That's the example of a prediction problem that you cannot solve. Because as if I give you a lot of entries and you don't see repeated entries, every new entry you observe has a random label. You cannot predict that problem because it's total noise. So in case one, the entries are at least somewhat predictable. You can predict them even with like 7/8 probability getting the right answer. And in case two, they're totally unpredictable. So this is like a prerequisite to solving matrix completion with noise, is that not only should you be able to find a good prediction, but you should be able to distinguish between models where there is a good prediction to be had and where there isn't one. So this is an even easier model. But now what I want to do is I want to connect this to random CSPs. And here's my main claim in this talk, is that this same identical problem was actually studied in two very different communities using very different terminology, but it was actually the same analysis. So one community was the community working on matrix completion, and one community was the one working on refuting random CSPs. So the first thing that I want to do is I want to take this model of random observations in M that are plus minus 1 entries, and I want to turn it into a CSP. And it'll be clear that I'll be able to go both directions. This is just an interpretation, but this is, I think, the hardest part, is figuring out how to translate freely between these two different worlds. So imagine that I give you an observation, which is ij sigma. And I and j are, it's an index into the row, an index into the column, and then you get this plus minus 1, random variable. What I claim is that you can think about this as a 2 XOR constraint, because that rank 1 term you're looking for, those AIs, well, you can think about them as having variables VIs, which are supposed to take on plus minus 1 values. I don't know what they're supposed to be. They're supposed to be equal to the AI and AJs, but I take the product of those two variables, and that is supposed to be equal to the corresponding constraint I observe. So this takes a second to think about it, because I don't know that vector that's showing up in my rank 1 part of my matrix. But when I take the outer product of that vector with itself, and all the entries are supposed to be plus minus ones, then the entries that I get algebraically are exactly XOR constraints, because I'm multiplying two plus minus 1 variables, and they're supposed to be equal to some other plus minus 1 variable that I've observed. And I claim that you can go the other direction, because if I give you, in this distinguishing problem, a bunch of random entries in your matrix, and they're all plus minus 1 values, and you're looking not just for a low rank matrix that agrees with them, but one whose rank 1 term is the outer product of a plus minus 1 vector with itself, then all of those observations are clauses. These are totally equivalent, but different ways to think about the problem. And we're going to get different intuitions from going back and forth between them. There may be questions on the chat. I'm not sure. And are there questions on the...
There was a question, what is CSP?
Yeah, constraint satisfaction problem. So here, for example, these are each the constraints, vi.vj, where those are variables that are supposed to take plus minus 1 values, are equal to this right-hand side that I was given. So that's just an example where each one of the equalities, we just call it a constraint. Sometimes it's like a SAT formula as opposed to something that's algebraically nice, like a product, like here.
There's another question now from Jordan Ellenberg, who says, I'm confused about the fact that the tensor is over R and not F2.
Mm-hmm. Right. So that's true. So I could make it over F2, but here I'm really thinking about the mapping between them, where I'm taking, an element in F2. Let's say I take 1, I'm going to map it to -1. I take the element 0, I'm going to map it to +1. So then when I multiply over R, I'm going to get the same thing as what's happening in the field. But these things will be sort of algebraically nicer, because here I'm talking about the special case where in this distinguishing problem, I'm looking for a rank 1 term that's the outer product of a plus minus 1 vector. But in the real problem, I'm going to care about real valued entries, and then there's no field that I can really map this to. So unfortunately, this entire problem this talk is about learning how to translate between these problems. And it's about translating between the observations and the clauses, and translating between, the real valued algebraic constraints and the things that are happening over GF2. But please stop me again if there are other questions about this translation. This is sort of the key to figuring out how to go back and forth. So now I have to tell you the second to last notion I have to introduce. This is, something that's very important and well studied within the random CSP community, and it's the notion of strong refutation. So I'll introduce it, and then I'll tie it back into this distinguishing problem. So strong refutation, you can think about, if you're given a random CSP, and by that I mean you choose the clauses at random. You choose a random variable for the first one, you choose a random variable for the second one, and then you put a random constraint on the other side, and you do that m times to create a CSP. Well, one thing that we could ask an algorithm to do is to refute the CSP, to show that if the number of clauses are large enough, to prove for us that there is no satisfying assignment. So in particular, what we want our algorithm to do is it should have the property that when we give it a formula, it's going to output some quantity value. It's going to work hard and compute this upper bound. And it should have the property that it's always an upper bound for the largest fraction of clauses that can be simultaneously satisfied in the random CSP. So it's always a faithful upper bound. But moreover, it should be good, because otherwise my upper bound could just be 1 always, and that's really boring. Instead, what I want it really strongly refutes. It shows me that this random formula is not even close to being satisfiable. In particular, I want the actual value that I output to have the property that if you feed it in a random CSP with enough clauses, that it spits out something that's half plus little o of 1. So what it's saying is that this algorithm would be given a random CSP. It would spit out an upper bound that always holds, whether the CSP were random or not. That's always an upper bound of the largest fraction of clause you can satisfy. And yet this algorithm would be close to tight in the sense that for a random CSP, it would tell you you can't beat random guessing. And that's kind of the key, is because we could use an algorithm for strong refutation to tell the difference between those two generative models in the distinguishing problem, one which has a good prediction and the other one which doesn't. So this is the hint at why these things are related, but let's do it more precisely. So what if I take this translation, which can go back and forth both directions? I give you this partially observed matrix of plus minus 1 entries. On the other hand, I give you a 2 XOR formula, right? And what I claim is that the spectral norm of A gives me a refutation. So it gives me an upper bound that always holds on the optimal fraction of clauses that you can satisfy. And this is, not hard. It's just a translation question. Why is this true? Because if I took a formula which had a good satisfying assignment, so it had a plus minus 1 assignment that satisfied tons of clauses, I could turn that into a unit vector, because I could create a vector x which has a plus minus 1 over root n for its entries. That would be a unit vector. And when I take the quadratic form of x on A, every time that assignment satisfies a clause, it'll contribute something positive to the quadratic form. Every time it gets the wrong thing, it's going to contribute something negative to it. So when it gets the right thing, it contributes 1 over n. When it gets the wrong thing, it contributes minus 1 over n. So in fact, whatever your gap is from how much larger than a half of the clauses you can satisfy, that's the thing that'll drive the spectral norm of A to be larger. This is the key idea.
There's a question from JM.
Could you remind us what this norm on A you're using is?
Sorry. So it's the operator norm.
Okay.
So in particular, here in this proof, all I'm doing is I'm saying, if you give me a formula phi, which has an assignment where you can satisfy 3/4 the clauses, then I can build you a unit vector so that the quadratic form on A is large too.
Just again, what is this quadratic form?
So it's X transpose AX. So if you give me a satisfying assignment, or if you give me an assignment to the variables for this corresponding CSP, I'm going to create a vector X, which the X sub I coordinate is I take whatever the ith variable is in my assignment to the 2 XOR, and I put that over root n. That's it.
Thank you.
So now we're in business, because we can just use random matrix theory, right? Now, let me be fast and loose with these things, but obviously there are plenty of tools that you can use. Well, what's going on is you have m random observations in A, and if m is large enough, like it's n log n, then m over n is the average degree. It's the number of non-zeros in a typical row or a column, and you would expect the random matrix A to have a very good spectral concentration. So good that it's approximately Ramanujan. And that would be square root of the degree. So you can check through whatever favorite matrix concentration bounds you want, the trace method, matrix Chernoff bound, that the behavior that you get for the spectral norm of A should look like square root of m over n.
There's another question from Jordan, who says, I'm confused about whether M is the number of entries of the matrix / tensor we observe, or the rank in the purported low rank model.
It's the former. So R is the rank of the purported, the thing we want to learn. M is the number of observations, and equivalently the number of clauses. So it's the number of non-zero entries in A. So you can do a little bit of algebra here, and if you believe me that the spectral norm of A behaves like square root of m over n, then what this will imply is that when m is like n log n, you're going to get the bound that you wanted. It'll be half plus little o of 1. That's the key idea. Because when I look at the right-hand side of this inequality, I get 1 over m, and I multiply that by root m over n, so I get 1 over square root mn. As soon as m is little omega of n, so it's growing faster than n, it's n log n, then what's going to happen is you have something that's smaller than 1 over n on the right-hand side. It's little o of 1 over n. And the only way that that can be the case is if opt is very, very close to a half. So this gives us an algorithm. We can solve the strong refutation problem for random 2 XOR, because all I have to do is you give me your random CSP, I turn it into a matrix, and I compute 1 over m times the spectral bound. That, and then I rearrange the terms in it. That'll always give me an upper bound on opt, and it'll also be good in the sense that it really does reach a half. So, that's a very simple algorithm in refutation, just using spectral techniques. But what I want to claim is that, this same thing was actually rediscovered in a different community. And, the same thing has been happening in matrix completion. So this is the last new notion I need to introduce you to, is that I'm going to show you that that same spectral bound, the spectral bound on A, is both an algorithm for strongly refuting random 2 XOR, which is the thing I already showed you. And it's also an algorithm for solving the distinguishing problem that, I'll just take for granted. But it'll also tell you that using the nuclear norm for low rank matrix completion is good. That same spectral bound is going to show all of these 3 things together. So let's go back to our convex program for matrix completion. We have this optimization problem where we look for the x that agrees with the observations so far on average. So the average over all of the observed entries is that it's off by at most a plus minus eta on average. And among all of those things, I want to find the x that has the smallest nuclear norm. And in fact, just to introduce you, this is why the story, I think people didn't see this connection, was because there are somehow too many different communities with their own language for these things. But, the way to think about this is that we have this optimization problem that we solve, and the x that I spit out after I solve it, I know that it's good on the observations I've been given so far, right? I know that the empirical error on the actual things I've observed is at most eta on average. That's just the constraint of the convex program. But what I really care about is the prediction error going forward, because maybe not just on the observed entries, but on all the entries of the matrix, I want the property that the average error between x, the thing that I get when I solve this convex program, and m, the thing that I wish I had, that should also be small. So, why does the empirical error being small imply that the prediction error is also small? Right? And this is a very classic topic. It's called generalization error in statistical learning theory. But the same spectral bound that was used to refute random CSPs is going to show up when we analyze generalization error. Because, as I alluded to before, there's this other view of what the nuclear norm is. You can instead talk about a description of the set of x's whose nuclear norm is at most 1. And as I mentioned in words, it's the convex hull of A, B transpose, where A and B are unit vectors. That is the set of all matrices whose nuclear norm is at most 1. And the actual nuclear norm is just how much you have to dilate to get inside that set. Now, the generalization error is the thing that people care about all the time in learning theory, especially in statistical learning theory, which is just the thing that you would expect. You care about the gap between your empirical error. That's the thing that's enforced by my constraints. The empirical error is at most eta on average. How far off can that be from my prediction error? That's called the generalization error. Now, there's a slight twist, which is that usually what you care about is you don't know anything about the x that you spit out other than the fact that it should have nuclear norm that's small. So what you really do is you look at the worst case gap between these two things among your entire set of hypotheses. So for any x whose nuclear norm is at most r, or any x whose nuclear norm is at most 1, you look at how much you expect this gap to be between the empirical error and the prediction error. That's called uniform convergence. And there's a really intuitive and beautiful statement, which is that the generalization error is bounded by the best agreement within your class, your set of nuclear norm at most 1 matrices, with a random function. See, because the richer your class of functions is, the more expressive it is, the worse you expect it to generalize, because it might be memorizing your data. But the less complex it is, in particular as measured by how badly it correlates with a random function, you can actually control the generalization error and show that my empirical error is small is not an accident. It's because I found a low description complexity way to describe my observations, where here the description complexity has to do with the nuclear norm. That's what makes the matrix nuclear norm good from a statistical learning standpoint, and that's what we need to find a stand-in the context of tensors. So this is called Rademacher complexity. So that's the last thing that I have to introduce. So what is it? Just unraveling this intuitive definition I gave you, is what you can do is you can take m random locations in your matrix. So what is a random function that I would want to agree with? I take m random locations and I put in random plus minus ones in them. Those are my sigmas, and they happen at the location IA, JA. And then I ask, what's the best agreement I can get among the family of matrices whose nuclear norm is at most 1? That's a complexity measure for this family of hypotheses about how well they can correlate with a random function. And I claim now that we're in good shape, that that's actually the spectral norm of A. Because, what is the set script K? It's the convex hull of AB transpose, where A and B are unit vectors. So in fact, if I take the sup and just look at all of the things that I'm expressing it as the convex hull of, then the sup overall little a and b, little b of AB transpose inner product with this sparse matrix with random plus minus ones. Remember, that matrix was called capital A, and their inner product between them, well, that would actually be achieved. It's always achieved by the singular vectors of A. So it's another definition for the operator norm of A. So Rademacher complexity, actually of the nuclear norm ball, is the same spectral problem that we used to refute random CSPs. Is the Jing Fen asked if is A here a matrix or a tensor? Yeah, this is all matrices because I'm not even doing anything new. I'm just reformulating two different literatures that had a missed connection. And Jordan asks, I'm still confused about the translation, but don't want to stop the talk if everyone else has it under control. Jordan, would you mind chiming in? And, I don't want you to be confused about the translation.
Thank you. Yeah, you already responded to this, was about whether M is the number of entries. But
okay.
Yeah, Jordan, right. If you have any further confusions, please feel free to.
Any further confusions, I don't have to get through that much stuff. There's not that much more anyways, so. This translation is the key thing, and it takes a little bit, I think. And that's exactly as Jung Feng was asking. That's why I'm doing it for matrices, because we're going to get a bit more complicated. But, we already bounded the Rademacher complexity. That was what we needed. That's what showed up in our strong refutation. So in particular, when you look at what the Rademacher complexity is, we know that it's little o of 1 over n, once we make M large enough. And what this means is that once you have enough observations, you cannot correlate well among the set of nuclear norm at most 1 matrices with a random sparse matrix. So this is making good on this promise that, I said before, that there are two very different communities that essentially attacked the same problem. Because what happened was that, in separate lines of work, on the one hand, people had this nuclear norm convex program, and at least one line of work following the Cerebro-Streibman style things asked to show why that's good in terms of generalization error and Rademacher complexity. And another community that wanted to refute random CSPs algorithmically. And the same spectral bounds are the things that control both of them, both the Rademacher complexity and give rise to an algorithm that solves strong refutation. Now, let's, make good on my promise. Let's use this connection to solve tensor completion. So we can do the same type of thing before, because, if I give you random sparse observations of a tensor, and I want to bound somehow the Rademacher complexity of some family of hypotheses that I'm completing it with, well, I would care about how rich that family of hypotheses is as measured through Rademacher complexity. So I would care about if I give you a tensor that's n by n by n, and I put in m random plus minus one entries sprinkled around, I would care about, whether the family of tensors that you're optimizing over, that low complexity measure, has low correlation with that set of sparse random tensors. And that, it turns out...
Sorry to interrupt. JM says, could you explain Rademacher complexity a bit more?
Yeah. So Rademacher complexity is, if you think about the optimization problem that I want to solve, I'm looking for, among all x's that agree with my observations in the sense of having low prediction error, I want to find the x that's the simplest in the sense that it has the smallest possible nuclear norm. So now, what really matters here is whether that's a big constraint. The fact that you have low nuclear norm means that you're not agreeing with being able to fit a random function. And it must be that you have low empirical error, because you found the right explanation. So Rademacher complexity is really a measure of how rich a class of hypotheses are. And this class of hypotheses for us are the set of all x's, which are matrices, whose matrix nuclear norm is at most 1. The way that we measure how complex that class is by asking how well they correlate with a random function. If they correlate badly, then they're a small class, and they must generalize well. If they correlate very well, then they have the capacity to memorize random things, and they might not generalize that well. So hope that makes sense. If not, please ask me again. So now we can move to the world of tensors, because this translation between having sparse observations in a third order tensor, that's actually the same thing as being given a random CSP. It's just that there aren't 2 variables in each one of the clauses. Now there are 3. That's where the higher order comes in the land of CSPs. And now the funny thing is that actually one of these communities did get a little bit further with this problem. So there's a work of Koya, Oglin, Gert, and Lanka that solves the strong refutation problem for 3 XOR. That's somehow the thing that we would need to solve if we wanted to complete tensors better. So it turns out that you can go the other direction. You can take their refutation for random CSPs and turn it into a convex program. So that's the reason that bridge is so important between these 2 worlds. On the one hand, completing tensors, and on the other hand, random CSPs. So in fact, the trick is kind of funny, because, what do you do with a 3 XOR problem? What do you do with a third order tensor that's sparse? You turn it into a 4th order one, or you turn it into a 4th order CSP. See, if I have this XOR constraint, this green hyperedge, which is Vi times Vj times Vk, those are all plus minus 1 variables, and I constrain that is supposed to be equal to sigma. And I have another clause, which is, overlaps in one variable. So it shares the same VI, and after that, it's got a different VJ prime and a different VK prime, and a different constraint sigma.
There's a question from Jen Feng, who says, thinking about this connection, is there an intuitive explanation from complexity theory for why 3-set is hard and 2-set is easy, i.e. why tensor is harder than matrix from the other side?
Yeah, so there are quite a few explanations, and they're really intertwined, I think, with, both like hardness of tensor nuclear norm and other kinds of things. But maybe I can table that one because there are quite a few ways to think about that problem. And I don't want to give too many of them right now because they're not really the subject of the talk. But if you could ask me at the end, then I can answer a bit more for that. But in any case, what I was saying was what we can do is we can reduce.
Before you go on, and Jordan asks, what does C dot mean here? And? Does it mean and between your two clauses?
Oh, I'll show you.
Okay, great.
Yeah. So remember that the VI, VJ, VKs are plus minus 1 variables. Same with the sigma and sigma prime, right? So these are 2 3 XOR clauses. I wrote them down. And as Jordan pointed out, I have the C dot in between them. I haven't told you what that means. Well, all I mean is we just multiply the equations. Now, when we multiply the equations, what happens? The VI squares, so it goes away. It becomes 1. So we get a 4 XOR formula. That's actually called, in the land of CSPs, it's called resolution. Because what you're doing is you're taking 2 clauses that are valid constraints on the satisfying assignment you're looking for, and you're creating new clauses. But in our land with XOR constraints, it becomes ordinary multiplication. For SAT, it's much more complicated, but this is what we're doing. So in fact, this is how I'm going to reduce 3 XOR to 4 XOR, is I'm just going to take pairs of 3 XOR clauses, which remember, those correspond to entries in the third order tensor that I'm observing. And I can take 2 of them that overlap in one index, and I can turn them into observations about a fourth order tensor instead. Or equivalently, I can take 2 3 XOR clauses and turn them into a single 4 XOR clause. Because literally, when I have this algebraic equation on VI, VJ, VK, VI, VJ prime, VK prime, when I multiply them, it's still an equation, but I get rid of a variable because I'm working over plus minus 1. Now there's a slight trick. Now, first, I want to give you some intuition for this, which is that if I think about P as the probability of observing a clause in here, so think about P as being like 1 over n to the 3 halves because I only want to observe about n to the 3 halves entries in my tensor to begin with. Now, how many times do you end up doing this step where you do a resolution step? Well, there are n to the 5 ways of figuring out how to map this diagram into my variables because there are 5 choices of what names to give these variables, what indices. So I get n to the 5th times p squared because both of those clauses have to show up. And if you substitute in p as 1 over n to the 3 halves, then you're going to get about n squared clauses, which is great because now I have a 4 XOR problem that has n squared clauses. If I took a fourth order tensor and flattened it into an n squared by n squared matrix, how many observations would I expect to need to be able to complete it? N squared. So that's where the magic has happened. But there's a big catch with this, which is that the 4 XOR clauses aren't uniformly at random because they come from these steps of resolution. And believe it or not, here's where a trick that might be familiar to you comes back to save us. And it's the magic behind this thing is that, see, when you take 2 clauses, one of which involves VI, VJ, VK, and the other one involves I, J prime, K prime, well, you've created this 4 XOR formula, and I'm going to flatten it into an n squared by n squared matrix. But the trick is that I take 2 variables from different clauses and mate them together to index the row. So it's not J and K that are indexing the row of A, it's J and J prime. And correspondingly, it's K and K prime that index the column. And then in this matrix, I'm going to put sigma times sigma prime. And I can try and use the spectral bounds that I gave you for refuting this random 4XOR formula. That's how Koya, Oglin, Gert, and Lanka refuted random 3XOR, was they turned it into 4XOR. And it's a very interesting thing you can do with sparse third-order tensors, is you can turn them into fourth-order ones that are a bit less sparse. And here I'm going to place the entry sigma, sigma prime. So the paired variables for the rows and columns come from different clauses. In fact, then what you can do is you can use the usual trace method to analyze these things. That's what they did. And we have some way of turning this magic into a convex program. That's really a relaxation for the nuclear norm, the tensor nuclear norm. That's provably good for completing third-order tensors. And I claim that this trick that I really harped on about J and J prime being on one side and K and K prime being on the other is really because of tensor networks, right? Because what I'm doing is I'm taking the legs of a tensor network. They share a variable in common. Those are the clauses. They overlap in a variable. And I'm pairing them up. And now the trick is that the way that I'm flattening it is it's the AB, so they're coming from opposite tensors, comma, CD flattening. And why is that nice? Because now when I take many copies of this, like when I multiply this matrix, which I've gotten through flattening many times and take its trace, then as I showed you last time, you get this very nice diagram, right? This is what happens when you unroll it 6 times. And the key is that this graph is 3 connected. That ends up being a big constraint on counting labelings over this graph, which shows you that spectral methods work for refuting random 3XOR using this resolution step. And that also gives you the state-of-the-art algorithms for completing tensors. So to a certain extent, there's a huge confluence of many different things that are going on here. So this is why I don't usually give this talk, is because it's hard. And I have kids, so it's kind of hard to have my brain function anymore. But there are so many things going on here as we're completing tensors. Somehow that's really CSPs in disguise, which is related to resolution, which is related to tensor networks, which is related to statistical learning theory. And all of these things are really the same language, at least when they come together on tensor completion, which is, I think, quite amazing. So as I alluded to, you can take this algorithm that you would get if you could complete random tensors. You'd get something for refutation, and you can go the other direction. You can turn it into an algorithm for tensor completion. You can use something called the sum of squares hierarchy. That's another way to use algebra to implement refutation and resolution steps. And you can get a good relaxation for the tensor nuclear norm that actually does solve the problem. Now, one of the funny things is that there are some blemishes in this result for sure. Because as I mentioned, one of the really nice things about matrix completion is that, when it's an exactly low rank matrix, then you get exact matrix completion. So what about an exact rather than approximate algorithm for tensor completion? So Potetchen and Stoyer showed that the answer is yes, but under a very strong condition, which is that the factors are orthogonal to each other. And that really makes it much easier to to create dual certificates of optimality, that the planted tensor is the optimal thing. Kiva and Potetchen recently got a much stronger result that works for random over complete tensors. Although I want to caution that random over complete, they won't be orthogonal factors, but they'll be nearly orthogonal. But it's neat that there are more of them than there are dimensions of your tensor. You could also ask, is there a practical algorithm? So it's kind of cool that this is a setting where there's an honest computational versus statistical trade-off between the n times r observations you would hope for completing third-order tensors and what we can actually do. But ultimately, it's based on solving a giant SDP, because I have to take resolution and embed it into a semi-definite program. I haven't told you how to do that, but maybe you'll believe me that it's not easy, and it yields a very big, albeit polynomial-sized SDP. And you can ask, is there something that's practical? So there's been a ton of work after this on giving faster algorithms that avoid semi-definite programming. There's a really nice work of Montanari and Son that uses spectral methods. It has a catch that it only works up to end of the 3/4. That's not such a big deal, but it also only gives approximate completion in the sense that it's a one-shot thing. You create some sort of matrix, you take a spectral decomposition, and it'll give you some fixed accuracy estimate of your factors. There are other things now which are based on non-convex optimization. So there's an approach of Kai et al., which gets exact completion, but it assumes that the factors are nearly orthogonal. So their pairwise inner products look like random vectors. And actually recently we managed to weaken this to just some sort of lower bound on them not being too close to being linearly dependent. So as long as you have a singular value lower bound on, how far they are from being linearly dependent, you can get away with n to the 3/2 times r to the 300 observations. So still not quite practical, but you can run these things. And one of the fun things is that you can actually complete tensors with up to 1,000 dimensions. So these are pretty giant tensors now because they're 1,000 by 1,000 by 1,000. So I'll roughly stop here. And what I hope you got out of this was that most of this talk was really about a translation, about how to translate these problems of completing low-rank matrices and tensors and turning them into random CSPs, at least in some very specialized versions of tensor and matrix completion. And I gave you new algorithms for completing third-order tensors that beat the naive flattening bound. But, and the way that we did it was we actually embedded these algorithms for strong refutation into some sort of algorithmic convex relaxation. So I'll close with, is practical tensor completion within reach? So thanks for your attention. Happy to take any more questions you might have.